This video looks at how to time orient the space-time inside the ring singularity of a Kerr black hole and the causality violation that occurs there in the form of closed time-like curves. It shows the conditions under which a massive particle can increase the rate at which it travels into the future. That's traveling along these time-like curves. Okay. Now in this video, I will refer to the previous videos in this series. So I'm just going to give summaries of past results as carefully as I can. But I'll continue to refer you back for the view of these. I'll refer you back to the details of previous videos. All right, so we're interested in the ring singularity inside the Kerr black hole, rotating black hole, and particularly the space-time within it. All right, now the ring singularity occurring in the equatorial plane is given by the equation x squared plus y squared is a squared, and z equals 0, so the equatorial plane here, and we're interested in the space-time within that. A here represents the angular momentum per unit of mass, and we have a coordinate system where r equals 0 is the ring singularity itself, r is greater than 0 outside that ring singularity, and r is less than 0, it goes negative inside. That's the coordinates we're using. Briefly here, we have the inner and outer event horizons here. The inner one is the green one, r minus, the outer is the red one, r plus. Stationary limit surfaces in yellow and blue. All right, and then the ergosphere in this region, and also over in this one. Okay, now coming back to the Minkowski spacetime of special relativity, we time orient our manifold, our spacetime manifold, as shown here. So I have Minkowski space in 1 plus 1 dimension. That's one time, one spatial dimension. And you can see the vertical lines pointing up the screen represent the vector field that is the direction of increasing time. Okay. So these dotted lines represent the coordinate lines. Tangent to these are the vectors ET, the basis vectors in the time direction. They point in the direction of increasing time. This is a time-like, they form a time-like vector field all over the space-time here, at every point of the space-time, and all pointing in the same direction towards increasing time, towards the future. This is a time-like vector field because it satisfies the condition with the inner product of the time-like vector basis vectors with themselves. The inner product dotted, the scalar product is -1 for the metric I use, which is -1 plus 1 plus 1 plus 1 on this channel always. Okay, I've shown one spatial dimension here, so we have 1 plus 1 Minkowski manifold. Now, this last condition, where this is a condition for a vector to be a time-like vector and a vector field to be a time-like vector field. This last condition shows that ET is also future pointing. So if you ever want to know if any given particular vector is future pointing, then what you do is you take the inner product of that unknown vector that you have, and you take the inner product of it with a vector that you know is future pointing, in this case ET, and if you get the negative result, given the metric I've described earlier, then you know that that vector that you have, whatever it may be, is future pointing. So this vector field we can show is not only time-like but also future pointing. Now the coordinate lines or the integral curves to this vector field are the dotted vertical lines here for the case of the time-like vector field. All right, so that's how we orient space-time, time orient the Minkowski space-time. And we want to look at now within the ring singularity, how we're going to time orient that region inside the ring singularity. So we can time orient the region of space-time with this canonical vector here. It's really the only combination of a linear combination of the time basis vector and the azimuthal angle basis vector. It's the only combination that gives you a time-like result, and all the algebra for all that's been done in previous videos, so please have a look at those. Okay, E alpha, we can express our basis vectors in basis form, or we can use the differential form. Okay, so the red lines are the integral curves to our tangent, to the tangent vector field v. So we have our vector field v, which time orients. This vector v points in the direction of increasing time. It points towards the future. All that has been the subject of previous videos. The algebra involved, everything has gone on. So please look at the previous videos in this series. Okay, the integral curves are these red lines. Okay, and the direction towards the future or future pointing is shown by the vectors v. This is how we time orient our space-time inside the ring's singularity. Now, just why is time-like important? Well, all massive particles travel along time-like curves, and both the t-coordinate and the phi coordinate are perpendicular to each other. So vectors in each of these directions are perpendicular. Okay, together this gives us a vector which is our time vector for this region. This is very different to Minkowski, because in Minkowski we only had ET, that was it. We didn't even have this scalar bit in the front. We just have ET. But inside the ring singularity, to time orient it, to show us where the future is, it's this vector we use. Okay, we can have a look at that here. If you look at the combination of the phi basis vectors and the t basis vectors, and we have a combination gives us a vector like this v, okay, at each and every point of this space-time. Now, in 3 dimensions, we could think of this, we could look at it, visualize it in a different way to what I've shown you in the previous page, ct, x, and y, okay, and we can see that in the xy plane, a particle traveling a circular path, as we'll be looking at shortly, okay, would be here. But when we add the time dimension, then this is the future. V increases this way. Going counterclockwise is the positive direction. This is the direction of increasing time. And so the opposite direction is the direction of decreasing time, moving into the past, going down the helix. So circular helix. So in 3 dimensions, picture this vector field as a circular helix. In a previous, the 3 dimensions being t, x, and y. In a previous video, we found the vector v to be time-like and future pointing. Again, go back to those videos for all the details. This means the integral curves to this vector field are also time-like, because the vector is tangent to it. V is tangent at all points here. The red curve is the integral curve of this vector field. Right, now, as we've seen in previous videos, there exist time-like curves within the ring singularity, and with one shown in green here. So here's our ring singularity. Here's a time-like path in here. Shown all that in previous videos, all the algebra, all the rest of it, the form it takes. We've shown that tangent to that vector field. So what we found is the time-like curve gamma, and then tangent to that is the 4 velocity, or gamma prime. Call that u or v or whatever you want. Direction of increasing time is phi moving in the counterclockwise direction, looked at from positive z. Okay, this distance here is a minus r0, because remember r equals 0 is the ring itself. Outside the ring is r greater than 0. We have 2 directions, which is very, very important now. Plus b in the anti-clockwise sense, minus b in the clockwise direction. When we're talking about time, direction is very important, because the future is positive, in the positive direction. The past is in the negative direction. In Minkowski space, you can only travel into the future. It's not possible. There are no world lines which take you into the past, because such world lines would lie outside your light cone. Again, all that's the subject of previous videos in this series, so I won't go into that. So let's say we have some sort of closed world line within this ring singularity here, gamma, we've called it. This little vector v is tangent to that world line. It's the 4 velocity, tangent to the curve there. Its speed, the scalar speed at each point, gives you a linear speed, that direction there, a linear speed which is given by this quantity here, multiplied by the angular velocity. or the angular speed. Okay, now the linear speed obviously must be less than the speed of light for a massive particle traveling on a time-like curve. Okay, this quantity B, we've defined that to be B as d phi d tau. Again, this is all the subject previous videos, so I'm just re-quoting results. Using the chain rule, d phi dt is dt d tau, which is d phi dt, the angular speed times the gamma Lorentz gamma factor here. Okay, or we could rewrite the Lorentz gamma factor as in this case, where there's two choices of B, there's a positive direction, there's a negative direction, we can have B as B times d phi dt inverse is B alpha inverse. Again, subject to previous videos, go through those. Okay, we take d phi dt, the scalar, as I showed you in a previous video, to be positive. And so it's just the B factor, the future or the past, positive or negative. Now just remember, CT is C gamma Lorentz times tau, or simply an interval of time for a distant observer, is the Lorentz factor times the proper time of some observer as observed by another. So the proper time tau, that's the between coordinate time and proper time. Here is the relationship between them. Our curve gamma, the green one on the previous slide, was given in this form. We could write that as this. Remember, it's fixed minus r0. It occurs in the equatorial plane, so theta is pi on 2, constant, and then b times tau. Okay, here we go. We can write that in these various forms. Again, the subject of the previous video. Now, a curve that would point in the past, we're going to have a negative b value. So we're going to put that in like this. Okay, a future pointed curve would go like this, a past one, that. All right, we found our particles world line to be this object here. Now, our tangent vector or forward velocity of our massive particle is, I'm just quoting results, just we can see is this one here. Okay, that there. And then from that, the reason I re-quote this is that from this forward velocity needs to be time-like. This tangent vector, so an observer traveling around our little green path we saw earlier, our world line inside the ring singularity, the tangent vector to that, which is the forward velocity, must be time-like for a particle with mass. And so what we require is that this tangent vector be time-like, which means the world line, the curve itself, is also time-like. So, okay, so here's our gamma written out in this form. The reason for that is, as in previous videos, I did all the algebra for this, but for this curve to be time-like, it must satisfy the following condition. And again, all of this has been covered in the previous videos. I'm just re-quoting the result here. This object here, dt d tau, the gamma factor squared can't be negative. So that means this quadratic here must be negative, must be less than 0 if we're to keep our curve gamma prime dotted with itself, the inner product, as time-like. We require this to be negative, and so that means this quadratic must be negative, and so that's going to have implications for the quadratic. We'll have a look shortly. We found in previous videos GTT is negative inside this ring singularity for small r0, as is G phi phi. So because this leading term is negative, we have a concave down, a parabola, if you like, that points downwards. It's concave down. The intercept is negative here. And so let's have a look at that plot. So the features of the plot for F, this thing here. Now, here's our intercept. This is negative, so there's our vertical axis intercept there. I've plotted this such that d phi dt against F, and doing that, I've plotted it between a linear. If you convert that angular speed here to a linear speed, you'll get the speed of light at that point. And the same up here, if you convert the angular speed here to a linear speed, that's what this c on a minus r0 is trying to do, is you're going to get the speed of light here. So these plots are going to be from minus c to c, okay, because there's going to be, remember, there is two directions. Okay, this intercept here occurs at this value here, the subject of previous videos, as is all these limits here, the subject of previous videos. I'm just re-quoting results. Okay, so here, if we look at this particular curve, it's time-like. Where f is negative, it is time-like, and a particle with mass can travel on a time-like curve. So it's very important. But it's only time-like from this value here, from this negative angular speed, angular velocity, all the way up to the intercept. At that point there, the curve becomes light-like. It ceases to be time-like. It becomes light-like. And then beyond that, the curve becomes space-like. Now, a particle of mass cannot travel on a light-like curve. That's not possible. So that's the absolute limit there. Particles' speed can asymptotically approach that value, but not equal it. Okay, and cannot reach that value. So a massive particle can travel here, but this angular velocity turned into a linear speed is much less than the speed of light. Okay, here we can travel arbitrarily quickly into the past because this remains a time-like curve right up to the speed of light itself, okay, at which point it ceases to be time-like. So for traveling the past, as I've shown in previous videos, we can reach arbitrarily high speeds close to the speed of light and travel arbitrarily quickly back into the past. And that's been the subject of previous videos. I'm not going through that again here. That's not the point. What I want to look at is this point here. There appears to be a limitation on how fast, or the rate at which we can travel into the future. There appears to be. Okay. This here, for the example I'm about to give, is about 0.81 c. Okay, so let's have a look at what that means. Okay, so let's take a 2.1 billion solar mass black hole with dimensional spin parameter 0.44, and inside the ring singularity, we're going to be about 0.1 of A, the distance A, 1/10 of the distance of A from the ring singularity itself. So that's about that distance here. When we plot that, okay, so here's our time-like curve, about 0.1/10 of the value of A from the ring singularity itself inside. Okay, now the intercept occurs here at d phi dt is approximately 0.002. So I think it was slightly a bit less than that, but approximately that's what it is. For discussion purposes, that's okay. That corresponds to a linear speed of about 0.81 c. Now, at this linear speed, the curve becomes, at that point, at the intercept, the curve becomes light-like, and for greater speeds, space-like, so no particle can travel on it. So this observer, massive particle, observer, spaceship, what have you, can approximate, can get near to the speed of 0.81 c, and then it's no longer able to travel on a time-like curve, and so that's its limit. And that's going to limit the rate at which it can travel into the future. Here, this curve is negative. It continues negative all the way to this left-hand limit here, which is equal to the speed of light over here. So we can travel into the past at an arbitrarily high rate, as close as we can get to the speed of light. And I've shown you that in previous videos. I'm not doing that again. Okay, but for motion in the negative direction, the curve is time-like. F is less than 0 for all speeds up to the value of c. So there's no problem there traveling into the past. We can travel rapidly into the past, as I've demonstrated in previous videos. It's just there's a limit on traveling into the future. And to give you some sense of that limit, let's have a look here. To travel into the past, we have b less than 0, which gives a world line of this form. This comes from the previous video. So for speeds, linear speeds, very close to that of light. We have, for example, if we could get 0.99, there's about 10 of them or something there, very, very arbitrarily close to the speed of light. Our gamma factor becomes 70,710.6, which means for 1 second of proper time for the particle observer in our spaceship, a distant observer will record delta t, and we'll find minus dt d tau, which is gamma times delta tau, is 70,710.6 seconds. If that same spaceship were to travel a month in their proper time, so an observer in the spaceship or a massive particle carrying its own clock would record a month of their own time has passed traveling this ring. A distant observer would claim they had traveled that many months, 70,710.6 months, or 5,892.6 years into the past. You can't do this in Minkowski space because there's no world lines which are closed. It's not possible. Okay, they would lie outside the light cone of an observer, so it's not possible for that to happen. These results hold so long as the curve gamma is time-like, and this is the case found in the video prior to this one. Now, let's have a look at the case of traveling into the future. So let's look at the region where the curve ceases being time-like. Remember that intercept there? This intercept is the point where the curve ceases to be time-like. It corresponds to a linear speed of approximately 0.801, about 0.81 c. Okay, it's linear speed at this point. There you go. Working that out gives you that. How far into the future could we expect to go at this rate? Well, our gamma factor here for that linear speed is about 1.7. Nothing like the 70,000 we saw on the previous slide for traveling into the past. Now, for an observer traveling for 1 month on this world line within the ring, okay, to a distant observer, they would only have traveled 1.7 months. So you're not going to move very rapidly into the future at that rate. Okay, there's a limit. This curve ceases to be time-like at about 0.81, 81% the speed of light. Below that speed, yes, you can travel into the future, but not at that speed. What we really need if we want to travel more rapidly into the future, not just 1 month for 1.7 months on coordinate time, we need some way of, can we make this curve more time-like for a greater range of values, getting closer and closer to the speed of light? Can we shift this intercept over here so that more of the curve is time-like? Okay, now it turns out we can by selecting a world line closer to the ring singularity. So by moving closer to the ring singularity, that's expanding, that's decreasing this value of R0 here, or increasing its value of A minus R0, okay, such as here, we're going to find a very different result. So we just need to make R0 smaller so that the world line, the massive particle, more closely approaches the ring singularity, as in this second diagram here, much closer to the ring singularity than this one. Let's have a look at some examples. Let's go back to our 2.1 billion solar mass, spin parameter 0.44, dimensionless spin parameter that. This time, instead of 0.1a, we're going to do 1,000th of that. We're going to divide that by 1,000, so we're going to have 1,000th of the distance, which becomes this. And what we end up with is a plot of f versus the angular speed of this object becomes here. Now here is the limit. It's plotted up, so it's arbitrarily, it's very close to the speed of light. So this intercept occurs at the angular speed divided t is that, approximately that, which corresponds, because I had to chop off some decimal places, so I rounded off a bit, which corresponds to linear speed v linear of this, which is about 0.995 the speed of light. So that's an improvement over 0.81 the speed of light, or 81% of the speed of light. This is 99.5% the speed of light. Okay, and you can see that much more of the curve is time-like now. It's in this negative region, so a massive particle can travel along it. Okay, so to compare the two curves, we've got R0 is 0.1a here. You can see the curve ceases to be time-like at this lower speed of about 81% the speed of light, whereas here, this curve ceases to be time-like at about 99.5% the speed of light. Okay, and that means that with these with this world line more closely following the ring singularity, we can access greater speeds closer to the speed of light to allow us to travel more rapidly into the future. Okay, so in summary, a massive particle such as an observer in a spaceship can travel at an ever faster rate into the future by selecting world lines both interior to and asymptotically approaching the ring singularity. Now I went from 0.1 of A, so 0.1 of this value here, and I took it down to 1,000th of that value, but I could go smaller again and get ever closer to that speed of light, and so boost the factor by which I can travel into the future. All right, that's it.